So I just want to focus in on these three here, because we didn't stop by just building this model, because this is interesting, but it's not actually revealing like the world secrets or anything like that. So we actually built what we call submodels. So you can sort of you can drill into these things. So which I'll do now. So, and again, it's going to be a spaghetti diagram, and this is actually a qualitative model, but I'm showing it to you as just a conceptual diagram, because otherwise it becomes really messy. But basically, so that we showed there was a relationship between sea temperature, reclaimed species, and commercial fishing. So we went to the community and got the people in the community to tell us how they saw that thing happening. Well, they said to us, okay, reclaimed species affects fish abundance. Fish abundance affects the price of fish. The price of fish affects profitability. Profitability affects the commercial fishing sector. So this is the pathway by which they saw this effect happening. So climate's not the only thing though that drives that commercial fishing sector. We wanted to put the climate into context. So what we did is we found out what else affects the commercial fishing activity. So the first thing that people mentioned was alternative income options. Because Australia is doing really well in terms of mining, a lot of the young guys are going to the mines to work. They can earn like $500–600 a day just working in oil and gas, just driving boats and things. So the fishermen are actually not getting free for their boats. So this was affecting commercial fishing activity. The other thing was that they said, well, we can't actually diversify our fishing. There's all these restrictions on exploring new things. So that's restricting fishing activity. One of the things that they also said was that in this particular case was access to fishing grounds. So that was, it doesn't stop there. Obviously profitability is, in their eyes, the main driver of their commercial fishing activity. And basically profitability is a function of fixed costs, which are the costs that don't vary by the size of the operation, the variable costs, which are the things like fuel, etc., and the price of fish. Those three will determine your profitability. So I just want to focus in on those three for a minute. The variable costs are the cost that people were experiencing fishing was largely the result of whether they own quota or not. So if they didn't own any quota, then they had to lease quota in to go fishing, and leasing quota in is basically more costly, so that was affecting their variable cost. So if they had to lease quota in for $20 a kilo, if you own the quota, you wouldn't have to pay that, so it increases your cost structure. Whether you own quota was really the result of whether your farmer owned quota and whether you was going to pass it down to you. But what was happening in the fishing industry is if you own the quota, people weren't able to pass it down to their offspring anymore because it was their superannuation, basically. It was their retirement income, so they had to actually hold on to it. So quota wasn't trading hands for this reason. Then the price of fish is affected by abundance, but also inputs and exchange rates. And fishing pressure is obviously affected through climate change, but also through fish abundance. So just to sum up, quota ownership characteristics were foremost in their mind in terms of how it affects commercial fishing. Quota trade characteristics were the second most. Work opportunities and exploratory fishing were the things that really guided this commercial fishing sector. Climate change, it wasn't really part of their decision-making processes. And they could see the path by which it could affect them, but it wasn't something that they were concerned about at the moment. But this model will help sort of, if we're going to do anything about addressing the issues of climate change, we have to know about all these other things, because otherwise we might be doing something that's completely irrelevant in the context of quota ownership characteristics. So it's important to understand how these things fit together, and if we want to use it for policy to change the system or improve it or make it more robust. So now I'll go back to the qualitative model that'll show you why it's important, why qualitative models can show you really powerful insights into what a policy implementation might do. So this is an example of the Ben Wiley, someone correct me now. Ben Weller.
Yes.
Yeah, okay. Thanks. Basically, they've got a hake fishery there, and the issue that hakes were the abundance of hake was falling. And they were saying, well, seals eat hake, so let's go and kill some seals. That'll increase the hake population. So this is a food web. This is the seals. There's the hake. Obviously, hake's not only eaten by seals, but other things as well. So simple qualitative model. We've got seals eating hakes, which hakes basically drive fishery. So we decrease seals, increase hakes, increase the fishery. That's the simple qualitative model. However, as it turns out, there's two species of hake in this system. One lives in the shallow water, and one that lives in the deeper water. So we also have juveniles and adults in our system, and we have juveniles and adults in the other species that live in the deep waters. So the adults of the shallow water one happen to eat the juveniles of the deep water ones. So what happens in the system, if we use a simple system here, we can say, yeah, let's go and cull some of these seals because they're eating our hake. So if we cull some, it'll increase our fishery. However, if we look into the system a little bit more carefully, we can see that the seals eat the adults here, that produce the juveniles, and the adults drive the fishery. Now, if we put in, these are the shallow water ones. Now, we put in the juveniles of the deep water fish, that's these ones, they get eaten by the adults of the shallow water one. The adults of the deep water ones that are producing the juveniles are over here, and they're also part of the fishery. So this is a qualitative model showing that system, right? Now what happens? Okay, we cull some seals, we have an increase in the shallow water hake, the adults, we have an increase in the shallow water juveniles. However, we have an increase in these ones, which means that we have a decrease in the juveniles of the deep water ones, because there's a negative relationship here, because they get eaten. So we have fewer juveniles that affect the adult population, so we'll have fewer adults over time, and these adults, as I say, are also fish. Fewer adults, fewer fish coming from the deep waters, even though we have an increase in the shallow water ones. So this system actually, and as it happens, with this particular fishery, 80% of the fish that were caught came out of the deep water. So killing the seals is probably not a good idea, because you're going to have a negative impact on your fishery. So this qualitative model, this more detailed qualitative model, would actually tell you, well, maybe that management approach is not such a good idea, because it actually will have a negative effect on the fishery. So that shows you some of the powers of just a simple qualitative model, which you could do on the back of a bit of a paper. Okay, so I just want to give you another, this is the third example, I'll just give you another quick qualitative model example where we incorporated a human and the biophysical system together. This is the banana prawn fishery. They had a problem, they had reduced abundance, and there was all sorts of theories about what was reducing the abundance in the banana prawn industry. So the qualitative model was built, so just starting from the bottom up, we have juveniles and adults again, we have a relationship there. The adults, there's the larvae become juveniles mature, right? So we have a predator-prey relationship here, there's predators of the prawns, and the prawns feed on food, so that's a qualitative model of that relationship there. Now we go and see if we can model that system. So we have adults, prawns, larvae, juveniles, and maturing adults here. They live in different parts of the system. These guys live offshore, these live in estuaries, and these live inshore. So this is your banana prawn biological subsystem that we're talking about now. So we have predators, each one of those, and we have nutrients that they feed on. And we have some competition for those nutrients in here as well, which is shown by that number. So that's our biological system. Now I'm going to put in the human system. So we have recreational fishes. These recreational fishes these are in the estuarine areas. The estuarine areas catch the predators of these juvenile prawns. The recreational fishermen out in the ocean, they catch the predators of the adult prawns. That's our recreational fishing industry. There's also a commercial fishing industry, which is shown by, there's two in this model. They catch predators of the adult prawns, and they also catch the prawns themselves. So our commercial catch system can be detailed a bit more. So catch impacts CVUE, but also affects the price of the fish. The more you catch, the lower the price. The price affects the efficiency and affects commercial catch. So we have a little subsystem over there. Now we put in the environment. Again. So there's turbidity in the estuary. So we have estuarine turbidity, which affects the predators in both systems. We have mangrove habitats, which affects the predators. We have rainfall events. Now these are the early rainfall events, and you probably know that prawns are like rainfall. Like if the fishermen see a lot of rain, they'll say, oh, it's going to be a good prawn season. That's a generalisation. So the rainfall, early rainfall has a positive effect on a number of these biological variables. Then we have late rainfall. This is a tropical system, obviously. We have late rainfall, which affects salinity, which affects the biological system through that pathway. So that's our model, which combines these guys with these guys and these guys. So, there's one more, sorry. Now what happens? I'm going to perturb rain. I'm going to say, okay, we've got an increase. We've had an El Niño year, and we've had lots of rainfall happening. So we've got lots of early rain. We don't have so much late rain, but lots of early rain happening. So what happens to a biological system? This is the mathematics that lies underneath it. Obviously gives us these results. It has a positive effect shown by the green ones. It has a negative effect on the predators through, so what you can see here is there's a positive effect on turbidity, which has a negative effect on predators. So a positive plus a negative is a negative, and the predators have a negative effect. A negative here means a negative effect. It also, surprisingly, has a negative effect on the price of the fish and effort. So this is the flow-on effects of the increase in rainfall. There's some that it has no effect on, obviously, and there's some where the effect is indeterminate, as we say, because this one is affected by the rainfall, but it's also affected by these two here, and we don't really know what happens there, what the sum total of the effects is. Okay, so that was, yes?
Oh, do you mind just going back to that one? In the PA circle, which is roughly in the middle, you've got quite a lot of positive and negative things there. So how do you assess whether overall it's positive or negative? When you haven't got any numbers?
Yeah, okay, so that's where the matrix algebra comes in, and this is where, because, obviously they're going to be lots of pathways by which that one is affected. It's a complicated set, and the bigger the system gets, the more difficult it is to establish those effects. But basically, the sum total of these effects here is positive, whether it's only slightly positive or not.
So do they have sizes, these effects?
So,
you talked about matrix algebra. Do the sizes actually have effects that are not shown this here?
yes. So it's a cumulative thing. So I'll have to show you probably afterwards because I can run the little program if that's going to help. It's going to be complicated to explain. Yeah.
But to me, qualitative implies no numbers at all.
Yeah, that's right. Just a positive and a negative effect. Yeah. But you can see that. Yeah. Yeah, it's a difficult one to come to terms with, but if you look at the matrix algebra, you can actually see how it is. Yeah.
So you think just plus ones and minus ones, that's the level of max.
If you just look at the signs around the circle, you see that you've got 4 circles.
Yeah.
And then you have two arrows.
Yeah. So
The overall should be positive, right?
Why?
why?
How do you know that? Because there are
Is
more
there-
positives. No, explain.
You have to
Just
count
visually, I'm just looking at
You count all the
you have to
pathways.
count
yeah.
all positives and negatives, there are even number of negatives.
It's a complex one, and again I can show you later on, but basically you don't just look at this one here, but you look at wherever that one comes from as well. So there's all sorts of intermediate steps, and these pathways can be really complicated and long. So it's basically lots of positive